Our topic is to discuss the relation of Cauchy's criterion, Bolzano-Weierstrass theorem, and monotone convergence theorem. So we will show that Cauchy criterion implies Bolzano-Weierstrass theorem, and Bolzano-Weierstrass theorem implies monotone convergence theorem. By the way, the reverse proof has been mentioned in the previous class, and so has the proof from monotone convergence theorem to Cauchy's criterion. So first, we will introduce the three theorems. The definition of Cauchy's criterion is every Cauchy sequence in real number converges. Bolzano-Weierstrass theorem is said that any bounded infinite sequence in real number has a convergent subsequence. And monotone convergence theorem is any bounded monotonic sequence in real number converges. Okay, and then we give a proof that goes from Cauchy criterion to Bolzano-Weierstrass theorem. First, we give a bounded infinite sequence an for any I belongs to natural number. We said that the upper bound of ai is u, and the lower bound of ai is L. That is, the sequence an is in the interval Lu. So we only focus on the interval Lu. Then we cut the interval Lu into half. The sequence is infinite, so one of them must contain infinite terms of an. And we pick one element from that half interval and call it A1 prime. We continue cutting the half interval into half. That is the quarter of interval Lu. By the same logic, one of them would contain infinite terms. We only discuss the interval having infinite terms of an, and do the same action. Pick A2 prime from that interval. Continue the progress. We get A2 prime, A3 prime, and so on. In fact, they are an infinite subsequence of an. We notice that for any n greater than 1, the distance of A1 prime and the an prime is less than the distance of less than the half of the distance of Lu. Similarly, for any n greater than 2, the distance of A2 prime and the an prime is less than a quarter of the distance of Lu. Inductively, for n greater than greater than the capital N, we get the formula. And so the subsequence an prime is Cauchy. And by Cauchy's criterion, which says that every Cauchy sequence in real number converges, So we get the subsequence an prime is convergent. Then we get the fact that any bounded infinite sequence in real numbers has a convergent subsequence. That is Bolzano-Weierstrass theorem. So we complete the proof from Cauchy criterion to Bolzano-Weierstrass theorem.
Okay, next we want to show the proof of monotone convergence theorem using Bolzano-Weierstrass theorem. And we can recall that the proof of 3 to 2 has already shown by our teaching assistant, Cauchy. Now, let's take a look at a sketch of a proof. Let's say we have a sequence that is increasing and bounded. Now, Bolzano-Weierstrass theorem says that we can always take a convergent subsequence of an. Now we need to recall that a subsequence won't change the order of a sequence. It's just canceling some terms in the original sequence. So the subsequence is actually also increasing. And the subsequence, since the subsequence is convergent, that is for any epsilon neighborhood of some of a real value L, we can always pick, say, big N that is big enough. So every term in the subsequence that has the index greater than n will fall into this interval. And since it is subsequence of an for also the say n from big enough, a the index for an greater than big N from an will fall into some of the terms in the subsequence. Say it is like this. So the an will also fall in the interval. And we can recall that the definition of the limits, it is for any epsilon greater than 0, we can always pick big enough n, so an will fall into that interval. And that is a sketch of the proof. Now we can see the formal proof. First, without the rules of generosity, can consider an is bounded, n is bounded above, and since it is increasing, it is also bounded below. So it is bounded. By Bolzano-Weierstrass theorem, it has a convergent subsequence, say it is a Rn, and we assume the ARN has a limit L. Now, by the definition of the limits, we can say for big enough n, ARn is in the interval L minus epsilon, L plus epsilon. Now, for any n that is greater than R big N, we can have this inequality. And since ARn is increasing, also AN is increasing, we can have this inequality. And since ARn has a upper bound L, and by the definition of limits, it is greater than L minus epsilon. So we can say actually L minus epsilon is smaller than AN, smaller than L, for n greater than R big N. And that is AN will converges to L. So any bounded increasing sequence will converge and similar to bounded below decreasing sequence.